This is Ramandeep Jindal, and I'm here to present the peer-graded assignment for Machine Learning Foundations for Product Managers course. Now, what's this assignment? We're going to build a model to predict the electrical energy output of a combined cycle power plant. We have been given a set of 9,568 readings from sensors, which will be used for model development. There are multiple columns in the data, which includes temperature, ambient pressure, relative humidity, and vacuum. And finally, the output is the net hourly electrical energy output, which is also the target which we are trying to predict. There have been multiple guidelines as well for us to proceed with this assignment, which includes defining the machine learning approach, selecting the output metrics, determining which features we're going to use in the model, identifying different algorithms which can be considered here, spreading the data to create a test set and the training set, defining the validation strategy, and using the strategy to compare at least two different models. And then finally, we'll be selecting the best model, which is the best based on the performance. Uh, on the model development approach standpoint, below is the approach which we've used. The first one is we have chosen to go with a multiple linear regression model. The reason we have done this is because we have multiple input features and which are processed to predict the target value. So multiple linear regression machine learning approach definitely works really well in this scenario. From output matrix standpoint, we're using multiple matrix, which includes mean square error, mean absolute error, mean absolute percentage error, root mean square error, and R squared. From the performance standpoint, when we compare the models, we'll use this matrix. Lower values of MSE, MAE, MAP, and RMSE matrix will indicate better performance, whereas the higher values of R squared will indicate better performance. We are using all the features like temperature, ambient pressure, relative humidity, and exhaust vacuum as the features for the model. There are multiple algorithms which can be used apart from multiple linear regression approach which you're using. These may include decision trees, random forests, graded boosting, or neural networks. And each of these algorithms has its own pros and cons and may perform differently depending on the data set. Uh, we're going to split the data between the training data and the test set. The split is done at a ratio of 80-20%. So 80% training data, 20% test data. From the validation strategy standpoint, we are going to compare two models based on a strategy which is employed based on fixed validation set. The test data, which is 20% of the overall data size which we'll have, is going to be the validation set. This subset of data will not be used for training, but it is only to assess the model's performance and select the best one. Finally, from the model comparison selection, we will create two models using the below approaches. The approach one is going to be use all the four features and build the multiple linear regression model. This model will be trained with 80% training data and will be used to compute the coefficients. Approach two, we're going to use these coefficients, identify the feature with the least coefficient and drop that feature, and then use the remainder three features to build the second model. Both these models will be trained using the same training set. That's 80% of the overall observation data, and maintain and ensure that we maintain the consistency. And finally, on the model selection, whatever model which performs best based on the output metrics will be selecting that model. Finally, on the model demo, we have built this regression model using Excel capabilities. And in order to do that, we have leveraged the data analysis back in Microsoft Excel to do the regression computations. Now I'll go over to Microsoft Excel to do a quick demonstration. All right, here we are on the Microsoft Excel. First tab, this is the main data sheet which was provided as part of this assignment. It includes our features and it also includes our output or the target column. There are 9,568 auto observations. From approach one standpoint, we are going to use all four features in the model, and this model is going to be trained with the training data of 80%, as we just recently talked. On the left-hand side, you see the entire same data set here. From the training standpoint, we're going to use 7654 for these data observation points here. When we run regression model for this data using Excel, and we've used the Excel data pack, which is as part of the Microsoft Excel. You can see analysis tool pack, and then when we go to data analysis, we can select regression. and it creates automated regression summary. And the core important point is going to see what is the R squared here, which has been automatically computed. It talks about standard error. It provides us different coefficients. You can see the intercept value, the ATV, AP, and RH values. Um, and we and if you see this data, you see the RH value is the least or the lowest value. So in our second approach, we're going to remove RH value and recompute or rerun this entire regression model to see how it has performed. So this is what we do in the approach 2. So if you see here, we don't have the RH value there. We have removed it completely from the data set. And when we run the same model using the same set of data, that is 7,654 data observation rows, you see the new R squared, which is 0.91855. You see standard error, and then you see the new computed coefficients, which does not include RH at all right now. So using these two approaches now, we're going to run our final validation sets using the 20% of training data. So what we've done is now we are going to pick up the first model, which has RH included, and run the different computations on MSE, MAE, MAPE, RMSE, and R squared using the coefficients which are derived from approach 1. And in order to derive these, well, you can see that all these data points with respect to predicted PE, which is dependent on ATV, AP, RH, and the coefficients have been computed. We have computed the error between the RH and PE. Sorry, PE and predicted PE. We've also computed the absolute error. We computed the square of error, absolute error percentage, and total square deviation from mean. And using these computed values, which are between F and K, we've actually derived MSE, MAE, MAPE, RMSE, and R squared. We repeat the same process for the approach number 2, which does not have an RH column now, right? So you can see here our input data set does not have RH. And we rerun with the same computations, but with the new coefficients, which again does not have an RH. This is again as part of the approach number 2. And for all this exercise, we are using 20% of the data only. And this is same data which is used in both the approaches, approach 1 and approach 2. So again, for this data, we have computed the new metric set, which includes MSE, MAE, MAPE, RMSE, and R squared. So finally, from the model selection standpoint, what we have done is we have collated together the data for our metrics. So you can see these metrics here. We have approach 1 and approach 2, and all the values for both these approaches from the metric standpoint. And as we talked, the lower values of MSE, MAE, MAPE, and RMSE will indicate a better performance, whereas a higher R squared value between these two models is going to be a better performance. Now, consistently, I mean, if you see approach 1 has lower values in all the first 4 output metrics as compared to approach 2, and R squared value is even higher in approach 1 than approach 2. So this is a clear winner. I mean, considering this data, it clearly shows that approach 1, which is running a model with all the 4 features, gives us a better performance using multiple linear regression model, and hence this is the chosen choice. This ends my presentation. Thank you for listening, and goodbye.